Right now, your computer is running a browser, a music player, a dozen background tasks, maybe a game, all at once. Except it isn't. A single processor core does exactly one thing at a time. One instruction, then the next, in a straight line. So 100 programs are somehow sharing a machine that can only pay attention to one of them. And not one of them freezes. And not one of them reaches into another and scrambles it. That should not work. 2 programs, 1 CPU, 1 pool of memory, and no collisions. How? The first trick is time. The programs aren't really running together. They're taking turns. The operating system lets one program run on the core for a few thousandths of a second. Then a timer fires, and the OS steps in and freezes it mid-stride. It hands the core to the next program for a few milliseconds, and then the next, cycling through all of them hundreds of times per second. It's so fast that from the inside, each program never notices it was ever stopped. It thinks it's had the processor to itself the whole time. The smoothness you feel is a flipbook. But you can't just yank the core away from the program. At the instant it's frozen, the CPU is full of that program's live state, the exact numbers it was working on, and the bookmark saying which instruction comes next. If the OS wants to resume it later as if nothing happened, all of that has to be saved first, copied out of memory, set aside. Then, the next program's saved state is loaded back in, and the core picks up exactly where it left off on that one. That save and restore is called a context switch. It's quick, but it isn't free, and your computer does it 1,000 times a second, all day. So taking turns solves time, but there's a second nastier problem: memory. Here's the thing. Every program is built assuming it owns all of memory, laid out in a neat line starting from address 0. That's baked in when it's compiled, which is fine for one program, but you're running dozens, and they all make the same assumption. They all want to store something at, let's say, address 1000. If those were real physical locations in your RAM, the browser writing to address 1000 would land on the exact same chip cell as the game's address 1000 and quietly smash it. Every program fighting over the same address. Total chaos. The fix is beautiful. The addresses a program uses are all fake. Every one. When a program asks for address 1000, that number never reaches the memory chips directly. Sitting between the CPU and RAM is a piece of hardware whose only job is translation. It takes the program's made-up address, we call it a virtual address, and looks up where that actually lives in physical memory. And crucially, it keeps a separate map for every program. So the browser's address 1000 gets translated to one physical cell, and the game's address 1000 gets translated to a completely different one. Same number, different destinations. They can't collide because no two programs are ever pointed at the same place. In practice, memory isn't tracked byte by byte. That map would be enormous. Instead, memory is chopped into fixed-size blocks called pages, and each program gets a table that maps its pages to real ones scattered anywhere in RAM. Looking through a table on every single memory access would be brutally slow. So, the most recent translations are kept in a tiny, blazing fast cache right on the CPU. The same trick that makes everything else fast. And here's the quiet payoff. That map is also a wall. A program can only reach memory its own table points to. There is simply no entry that leads into another program's pages, so it can't form a valid address into them, even if it tries. Isolation isn't a rule the programs agree to follow, it's a wall they can't see past. So step back and look at what every program actually believes. It thinks it has the processor entirely to itself, running smoothly from start to finish. And it thinks it owns a clean, private stretch of memory all its own. Both are illusions. In truth, it gets the core for a few milliseconds at a time before being frozen and shelved. And its memory is a fistful of pages scattered wherever they happen to fit, walled off from everything else. The operating system spends its whole life maintaining these illusions, millions of times a second, for every program at once. That's the real answer. 100 programs don't avoid crashing into each other by cooperating. They never crash into each other because not one of them can tell the others are there.